system, it was a distributed system that enables mobile devices that experience quite frequently disconnections from the internet to collaborate, form a network, and share resources. So one facet of this cooperation was the bandwidth sharing, where one device that had, let's say, Bluetooth or an access to the wide area network could share its link to other devices that didn't have access to the infrastructure. Another facet of cooperation was the information sharing. And the hypothesis behind that was the spatial locality of the information. That is, these devices that they are running location-dependent applications, or they are providing information for location-dependent applications or collaborative applications, had a lot of overlapping of the information that they wanted to access. For example, devices in close proximity, they wanted to query for similar data. This is the hypothesis of the spatial locality of the information. So essentially, this system was enabling these devices to act as miniature caches and share resources. An extension of this work, and with John Check, what we are doing at UNC is building different types of applications. So there are medical-related applications. There are some not sharing applications. At UNC, there is a lot of interest for virtual reality applications. They have a lot of different projects. So we come from the perspective of the wireless, of the systems, to help them set up these virtual games or virtual reality applications. Another work related to this spatial locality of the information is the positioning, the location sensing that I'm doing with high-speed IaaS. And there, the main idea is the following. Essentially, you have the devices that they don't have a GPS, or they have intermittent access to the infrastructure, to a location sensing mechanism. So what they do is, essentially, they collaborate, they share positioning estimations, and they use a map, a kind of map, where the main task is to try to assign different probabilities on the map about the location, about where is the likely position of this device, and then enhance this or change these probabilities as they receive positioning information from the peers, from the other devices. Another work is related to the energy conservation, and then the main idea is that we try to enhance a multi-channel protocol, a MAC protocol, where essentially when a device, each device can switch to different channels, can scan the channels, try to estimate the conditions of each channel based on its own measurements or measurements from other hosts. And then decide if it should remain to the current channel or switch to another channel that there is more bandwidth available, or there are no malicious users. So the problems are the trade-off between reducing the delay, the response delay that a host experiences when it loses the receivers that they were in the current channel in order to go to a different channel to save some energy. But today, the main focus of my talk is one of my latest projects. And this is a measurement project on the wireless networks. And this is work that I have been doing with Francisco Chinchilla and Mark Lindsay. Mark just graduated, but a new postdoc joined my lab, Felix Hernandez Campos, who will start participating in these measurements. So I should also say that UNC has a traditional measurement studies. They have been doing a lot of networking measurement studies, and it was an excellent opportunity for me to join that department because they really supported my study. And it was not an easy task because, as you're going to see, we receive extensive traces from all over the campus, from a very large number of access points, and we really need a lot of support, not only the test bed, a sophisticated testbed to acquire the data, to do the data acquisition, but also to have support from the systems administrator group. And they're really extremely important and very helpful to my research. So, as you know, the way that the wireless infrastructure has been deployed really impacts the way that users access the information. And you see a rapid growth of different wireless infrastructures, especially with the 8.11, not only in the campus, but also in medical centers, in the metropolitan areas, in institutes, at the airports, etc. Now, in cellular environments, there are traces that where you can use to analyze the way that users access the cellular infrastructure. But there are no such studies for the 8.11, for these wireless networks, for such large infrastructures. But however, we can get more traces now. It's easier to get traces from 8.11 infrastructures and study the movement pattern, the access pattern, the information that wireless users are accessing. So one motivation for me was to try to find more accurate, more realistic movement patterns and association patterns of users in such infrastructures. Try to answer questions like, how can really describe a continuous wireless access to the infrastructure? What are the durations when a user is associated at an access point? When the user gets disconnected, either with an explicit disconnection from the infrastructure or because it lost the signal from an access point, how can model this disconnection durations? Can we predict the trajectory of a continuous wireless access? So basically the trajectory of all these associations of a mobile device. And when we study different, the wireless access in different environments, how they evolve? What are the spatial and temporal properties of the wireless access? How can describe them? And how can contrast the different environments? So how an environment in a campus differs from a medical center or an institute, etc. So one motivation is to be able to describe the access and provide models for simulations. Because how you can do an accurate performance analysis via simulations if you don't have the proper models to describe the traffic or the association patterns, etc. So before going to some more motivations and the thesis of this research, let me give you just a description of how a typical wireless infrastructure looks like. So you have essentially an aggregation point, a router, and you have all these different clouds, the access points, the wireless LANs to connect through a switch to this router. And as I'm going to describe later, our monitor device, one of the monitor devices for the traffic, sits at the router. And then we have also a syslog server that receives the syslog information in order to be able to describe the movement or association patterns. But I'm going to give more information about that a little bit later. But here you see that the user B, let's say that he was at some point disconnected. Then he starts getting associated to the access point 1, and then he's roaming to a second access point 2, and then a little bit later to an access point 3, and then he gets disconnected, again, for different reasons. So what we propose is a very simple way to describe this continuous wireless access. We call it session. Okay, so the user B can have, of course, each user can have several sessions. And this is a kind of chain, right? It has different states. Each state corresponds to a visit at an access point. So at time t1, it was connected to the access point 1, and this corresponds to the state 1, and then to the access point 2, state 2, etc. And then you have this logical state, the 0 that indicates the disconnection. So we receive this through these syslog messages that the access point sent to our server. We receive information about the associations, and then these associations and the authentications of the different clients. Okay, and based on them, what we do is we pass and we construct, we generate these sessions. Okay, so a user can have, as I said, several sessions, and then we try to classify the sessions, characterize them, classify the clients, the users, client or user, I'm going to use these words interchangeably, in different categories based on the metrics that we define to characterize these entities, namely visit and session, and some more specific metrics. Now, I'm just going to leave this slide, but I'm going to go back again and describe some more about this. So, our thesis, and this is a kind of more general thesis for this work that also motivates us, is that we believe that both application and also infrastructure designers can exploit our characteristics, the characteristics we are going to present today, and we are actually investigating currently. And exploit the trajectory and the duration estimations in order to support this infrastructure, to support the access points or the proxies or the servers that they are installed in this infrastructure, so that they can do better caching, more intelligent prefetching, graceful handoffs to deal with the mobility that exists, some perhaps resource reservation at these servers or access points, to be able to provide better quality of service, to do a capacity planning. Now we are moving to a different time scale in order to make sure that there is sufficient wireless access, that there are no hotspots, that they deal with the loss of signal or the issues of the intermittent connectivity that potentially users experiencing in this infrastructure, to do potentially a load balancing of traffic, where an access point is intelligent enough to give some hints to the mobile client. Say, you know, I am overloaded now, but my neighbor access point can serve you better. So essentially, our motivation and what we believe that it can take place is to take the results of our analysis, some of them are going to present them today, and use this knowledge in all these different situations, in all these different scenarios, to be able to support these applications. And I'm talking about applications who have real-time, for example, constraints. So we have these virtual reality applications at UNC. Currently it's on the wide network. Okay, so if you want to move in a larger space and have the wireless use the wireless infrastructure, you cannot deal with very high delays, like for example the 150 milliseconds that we measure to access, to authenticate the device and access the infrastructure. Or if you have a location sensing system for a user with disabilities, that we have the prototype at UNC, you need to deal with all these requirements of such applications. It's a location sensing system, and not only, it provides multimedia data to users as they move, as they navigate to the campus. So today, my work will be based on our Infocom paper, and you can find this online, and also a new work that we recently submitted a few months ago with some collaborators, Harpreet Shen, who is a statistician, and really helped me in the analysis of our traces, and Manolis Panakis, who is a graduate student from University of Crete, and this is a place where we have a lot of collaboration.
We will actually be visiting here soon for a semester.
Yes, so hopefully you'll have him as a guest sometime maybe the summer or next semester. So let me give a very quick overview of this talk. I'll be giving now more information about the wireless infrastructure and data acquisition process, and then I'm going to briefly describe our results on the information locality. Then I'll give also an evaluation of the caching paradigms that we have been studying, and then basically concentrate, and the last two are the main really focus of my talk today, on the prediction of the next association of the access point and characteristics of the session. So essentially, how can models for the continuous wireless access of a user? This is what the session is. And then the duration that the user is disconnected. So of course, you know, UNC is a very diverse academic environment. It is located in 729 acres. In this study, we include access points from 77 buildings, all different types of buildings, and this is going to be an issue that I'm going to describe in the talk, how the building type affects the association patterns, etc. In this specific study that I'm describing today, we had 222 access points, but there is a larger number of access points included in the current study, more than 500, around 8,000 distinct wireless users, more than 8 million HTTP GET requests that we are using for the locality evaluation, the caching evaluation, and also more than 8 million syslog messages that we will be using for the association and movement pattern. So, basically we're monitoring all the wireless infrastructure. You really need a good support from the systems administrators to be able to get this data. And, I'm very thankful for them. Okay, so...
8.11.
Yes, everything is 8.11 in this wireless infrastructure. But as I'll mention in the future work, will be, and of course, this is in a campus environment. We are trying to contrast these measurements and this analysis with other results in different settings. This is another goal. So okay, this is not really the focus of my talk today, but I want to give you also some results on the information locality and the caching paradigms. And essentially the reason that I did these measurements, what we observe, again, in the same infrastructure is because when I was doing my PhD, I had this hypothesis that I mentioned to you earlier about the spatial locality of the information, right? This is what I was assuming, and it was a very strong hypothesis. And I really wanted to measure this hypothesis, how realistic it is and how it differs in different settings. And this is an area where I had the traces, right? So that was the first question that I wanted to answer. Although, of course, I didn't expect to see high spatial locality, because obviously the web browsing is not the most location-dependent application, right? But at least we provide the methodology that can help us to extend the study when you use location-dependent applications. And then I'll show you how we could evaluate the different caching paradigms. For example, the user browser cache, the same access point cache, the peer-to-peer cache, or some extension of these caches when you use a cache at a building where essentially all the HTTP GET requests through access points of a building can be served by this same building cache, or the extension after that, the campsite cache. And this is the very first study that on the wireless network, on wireless networks, and in this scale was studying these locality properties of the information. So this is some results to give you an idea. Let me first describe what you see there. So in the x-axis you see the time, right? And it is in a per day interval, and in the y-axis you see the additional repeated requests, and we evaluate different caching paradigms. So for example, if we let's try to interpret a point, so you can observe the red line where you see the results for the same user cache, right? A cache essentially of your web browser. Okay, how it performs. And the very first point here at the top, the 44%, what really, the way that we can read it is that there are 44 repeated requests that within a day interval that could be served by a user, the local cache. Whereas if we go to the brown line, which is exactly the second line, that it is close to the 7%, essentially there, the way that we can interpret this is that within a day, there are 7% of the requests that could not be served. There are 7% of requests that cannot be served from the user local cache, but can be served from the access point cache. So essentially a cache that could be attached to the access point. So when the access point or the server that has this cache gets these HTTP GET requests, it can serve them. It can respond with the web pages. A similar result you see when for the requests of the peers. Now, I would like also to clarify something. When I said about the impact of the peer-to-peer caching, what I really wanted to say is that peers in close proximity, that was ideal. Peers in close proximity that have the data can serve the other peer that sent a query, right? By sending the web page. However, we didn't have any simple way to measure the proximity. For example, we didn't have any location sensing system. We didn't want to install any other system that could really indicate the range between two peers. So the only way to answer this question, not even very well, but at least to be close to this question, is to try to use the correspondency metric. That is, if two clients are connected to the same access point, we call them peers. Okay, so what you see here with the green line is really if, and this is not always the case, but if two peers correspondent. If one peer was sending an HTTP GET request instead of going to the server or instead of going to the access point cache, if there was another peer associated with the same access point and had the data, could serve it by setting this web page. And you see the repeated requests here. Now, the other points across the line show you the additional repeated requests. So, for example, the second point shows you in the second day what are the additional repeated requests that you could see for the other, in all these different schemes.
Something about the diagram
Yes.
here.
Mm-hmm.
So you go over time for 24 hours, more or less. Yeah? And so what does the ordinate indicate? So if I pick the point 10 in the
Here?
horizontal axis, what do I see? What
Yes, so what you see here, yes, so what you see here is that at the 10th day, on the 10th day, yes, this is the day interval, yes. So at the 10th day, you'll see that there were around 0.04% of additional requests.
Yeah.
Okay, that could be served by the peer and couldn't be served from the same user or the access point cache. So the reason that I have this intersection, although in the paper, of course, you can find just the access point corresponding user or just the same access point. The reason that I have this intersection in this specific plot is to show you that if you could visualize it as a kind of cache hierarchy where a request first can be served by the local user cache. Then if there's no web related data in the local cache, it was sent in the access point cache. And if the access point cache cannot serve this request, it forwards this request to the peers. Okay, so and this is of course, making several assumptions. For example, that all the peers are cooperative, that all the items are cacheable, that no items expire, that there is a lot of storage in these caches, So we assume that. So essentially, what we study here is the ideal hit ratio. Okay. What we observe here, one of the first things that you can see is that there is a very high temporal locality, right? There is a 44% of the requests. We also saw a lot of periodicities, different types of periodicities in our traces. The other thing that you can see is that these two caches can be, after the second day, can be really very close, can perform, all these three caches have similar performances after the second day. Yes?
What you explained and what I shared. On the 10th day, that number, 0.44%, is the number of additional requests during that day.
Exactly.
That can be served by the cache or cannot be.
That can be served, yes. So basically, if you wanted to see what is the total number of requests that have been served until that day, including that day, for the different caching paradigms, you need to sum up, of course, take the area.
So why are they all decreasing?
Yes, this is related to the temporal locality. So we see that there are less repetitions. So the larger number of repeat requests are going to occur near each other, and this can happen because of many reasons. For example, it's typical, and you can observe that when you change the time scale to be a smaller, finer time scale, the servers quite often resend the data every 30 minutes or every an hour. So or there is the user behavior periodicity. Like, for example, every time in the morning you visit the New York Times website. Well, this is one periodicity, but there is also the other trend that you tend to visit the same site in similar days. For example, when you want to watch a certain event, and after some days, your interest declines.
I understand the periodicity, but what the decline I still don't see.
So there is this temporal locality that we observe. That is that. For certain web pages, for example, it appears that all the requests of similar users, the same user or co-resident users, they appear very close in time. So, for example, if I receive a mail related to some news at UNC or in Maryland, many users are going to get this information, going to access this information in close, at the same time, the same day, for example, or in the morning. And this is not a new result. I have seen this result in other studies over the web traffic.
It's not clear to me what we represent here, because you say that the first day is when you see, but why is day number 1 of your trace, that important day where you had all these many additional requests? Why do they over time?
Okay, maybe I should clarify that. This is not the first day. Okay, so let me describe how we get this data. So what we do is, for every HTTP GET request that occurs, we have the timestamp, right? And then what we do is, in order to be able to essentially create this repeated request, we go back on time and we see when the same request appeared before. And we keep track of when it happened. So the one day doesn't mean necessarily the first day of the trace, but rather that within 1 day interval, and this can happen in the 5th day or in the 6th day, the number of repeated requests for this specific web page were this. And then what we do is, then we say, like, for example, for New York Times, during the entire tracing period, had this many requests within 1 day. Yes, or within an hour. Actually, we just capture the difference when they occurred. So then we sum up all these requests all these repeated requests that they occurred within an interval of 1 hour or 1 day in this example.
So this time here is not really time evolving.
Exactly, no, it's not time evolving, but rather within a time interval, it's an interval. Yes?
In your setting, you assume that you have a peer and you have an access point and another peer,
yes.
Right? So the hierarchy for this search is first you search on your peer, then if it is not there, you go to the access point, right? Then if it is not in either of them, then you go to another.
Yes, this is, yes, just 1 second, let me clarify something. And exactly, this is the hierarchy that I'm assuming in this plot just to illustrate the intersection. But these are ideal, these are concepts, right? The caches do not exist. But we said, if these caches or the caching hierarchy, as you mentioned, exist, these are the repeated requests that we are going to observe.
Yes, but my question is, suppose the query that comes, you cannot find it in your own cache or in the access point.
Yes, yes.
So then, what is the probability that that query is in another?
Yes, this is what the graph says. The probability is that in these cases, the blue line answers your question in this time scale.
But shouldn't it be dependent on the storage policy that you want to use, how you store these queries in your access point or in your immediate users?
Yeah, sure, yes. I mean, it depends on exactly how you have installed this system, right? How you have configured. I mean, what is your actual cache, how your actual cache looks like. This plot, and you can find some more information in the paper for different types of hierarchies, reflects what you just described. That, for example, if the order that you first ask your local cache, and then you ask the access point cache, and then you ask another peer, assuming this order, the answer to your question can be found in the blue line. But in the paper, you see, if you didn't have this cache hierarchy, but rather you immediately ask the peer, you didn't have a cache locally at the device, you didn't have any cache at the access point, but only the peer, then how you could, what is the probability to answer, and which is, the hit ratio was something like 23% or so. But you can find the actual number in the paper. So this is some of the results that we noticed, but again, more information exists, more detailed information we can find in the paper. And we saw, one of the results is I mean, two are the striking results. One is that there is a very large, dramatic variance in the different caches across the campus. So it varies from 15% to the 75% of the overall hit ratio that we observe in these different caches. Also, we observe that by having an expiration time of 1 hour for the different objects, a large number of requests could be served. Also, that it could help a lot if we keep an access point cache, especially in certain buildings. And the other characteristic that we observe is that the numbers that we found are around 10% higher than the numbers for similar environments, for similar populations in other studies on the wired network. Now, going back more towards the side of how users are associated in the infrastructure, one question that we ask is to find the revisit probability. So, for example, when you have a client who is associated with an access point, what is the probability that this client can get associated to the same access point within an interval of time? And we observe that this happens quite often. And it makes sense in many access point cases to have a cache, to install a cache there of a lifetime of 1 hour. Now, these are very general results here for the revisit. So we wanted to be more specific, to be able to better predict the next access point, the next association of a client. Okay, so before doing these predictions, let me go back to the session characterization and give some more information on this. So you remember that we described the session, and we call this session access point path, because it is a path that it consists of all these chains of access points, visits to access points. Using this session, this entity, we can also describe the building path, where if, for example, you have that the access point 1 is at the building 51 and the access point 2 and 3 are in the building 7, you can have the building path. And one way is to try to find metrics to characterize these sessions, these paths. So, for example, the unique number of access points, the unique number of buildings, the path distances. So, for example, the path distances, we know the building location, so we can find the distances between two consecutive buildings in the building path, and then we can sum up these distances to find the building path distance, or the duration, which is the total duration of the session. Another metric is the range. So, for example, you can take the pairwise, the maximum pairwise distance of two buildings within a path. They don't need to be consecutive, and this gives you an estimation of how far a user traversed, was roaming in the wireless infrastructure before he got disconnected. Another metric is the if there is no unit, it's just a number, and actually it's the number of edges if there's no unit. So, for example, the unique number of access points. Yes, what I really meant here is the number of edges. If you see the access point path, and you count the number of edges, this is the access point length. The LCFS means longest cycle-free subpath. So this is another estimation to see how far the user goes with respect to inter-building transitions before he gets disconnected. And so these results give you just an idea. I'll be more specific to say that the well-defined sessions, okay, because we had, of course, hundreds of thousands.
There are some things that puzzle me.
Yes.
Building path length.
Yes.
The median is 0.
Mm-hmm.
What does that mean?
That means that most of the buildings didn't have any transition to two different buildings. So most of the sessions happen to access point within a building. So there are 0 edges. So when you...
The median value. So there is a mean, there is a median, there is a maximum and a minimum. I'm just focusing on that.
The median mean, yes. So, okay. So you have all these building paths, right? For all the sessions. So you count how many edges you have. Again, in the building path, you talk about the inter-building
So there is 1 or 2 or 3
right.
or 0.
So the median is 0.
That means that half of them did not.
Exactly. Yes.
But then, okay, all right.
So it is. So we did observe that a very large number of the sessions were a kind of sessions. I don't want to call them stationary, because stationary sessions are only sessions that occurred within an access point, but they're sessions with not a lot of mobility. But this actually leads me to a different issue, which is how you describe really the mobility, what mobile means. And we don't have you have to remember that we cannot afford to have a location sensing, a positioning system here for the trace, because it's expensive and it could complicate our experiments a lot. And there are also the privacy issues. There are many issues to worry about. So we're trying, using these metrics and these formulations, to describe the mobility. So I found that one of the most adequate ways to describe the mobility is using the range and a threshold on the range. The range here gives you, again, what is the maximum pairwise distance of 2 buildings in the path. And we found that the mean ranges, the mean and the median range is a little bit more than 300 feet. Okay.
How do the 2 tables differ?
Okay, I'll describe exactly. So when I told you that we have this session generation process, right? We need to construct from the traces, from the syslog messages that we receive from the access points, the sessions. And then, of course, we have hundreds, thousands of sessions, but we wanted to filter some of them for which we are not very confident, for many reasons. The most important condition, requirement, is that these sessions, when we had in the session generator, when we are constructing the session, it comply to the 8.11 state diagram. That was one of the requirements. Another requirement would be when the session ended, and if it ended successfully and properly with messages like syslog events that we understand, and they are common throughout all the different clients that we could have, because we didn't have only Cisco clients, we had a large number of clients. So we wanted essentially to clean the data as much we could. So we are really very strict. Well-defined session means the sessions that are really very clean, and we are confident that these metrics that we are presenting mean something. The mobile sessions, our definition here and throughout our talk today, the mobile session is all the sessions that had at least one inter-building mobility. A different definition would be on the threshold of the range. But we have some more results on the paper. I'm not going to go, I don't have the time to go very far on this. Yes?
Building pattern, for example, the maximum routing is 248. So you think that the user has visited 248 buildings during the session?
You mean building path? Show me where exactly. Building
path length.
Building path length. Yes, here you talk about the maximum, right? Yes, we did have. Oh yes. There were. We noticed some strange things, and I can describe some of the impact that they had on our results. But we did observe these users. Yes, I mean we tried very deeply to analyze all the strange numbers that we got, and whatever I'm presenting, we found these cases. So, for example, there were users. So, and this is not really very strange. I can give you an example. A possible explanation. I'm not sure exactly about this number for this specific user, but we observed several users that what happened was that, because you see, they had this a lot of switching back and forth from one access point to another. It happened to be in 2 different buildings, the access points, but the user may not even move. Just the signal strength was changing, and which was forcing the Cisco client to switch, to reassociate rapidly. So one of the main concerns in this study was to try to see where is the mobility. We talked about associations patterns, but for movement patterns, there are many situations where we may not know if there was actual movement because of the lack of the location sensing system. So we are trying to interpret, So that was a kind of challenge in this work. So I'm going to give some more information, but I'm just 1 second. So what we wanted to see is how many mobile sessions we have, how we can classify the users based on their mobile sessions or these values. Can we be a little more specific to model these durations? Apart from just talking about the averages and general statistics, that was another concern. And basically, how the different, for example, visits are in a session are distributed. we had several questions on this. This is just a simple graph that shows you the percentage of the mobile sessions, again, the sessions that had at least one interbuilding transition, as they are distributed across the clients, the different clients. So you see, well, the first thing that you can observe is that most of the clients really have very few mobile sessions. This is not very surprising because we didn't even watch many mobility within the wireless infrastructure. But an interesting point to observe is that there is a small cluster of users that they are really very mobile, and most of their sessions, so I'm referring to the last here, oops, they had a large number, more than 90% of their sessions were mobile. So we did observe a small cluster of highly mobile users. Now, a little bit more specific, can we predict the next association? What is the access point that this user will be an associate after the current visit? So we show that we can do very well, and even using some simple algorithms. So for example, if you model this session as a Markov chain, and basically each state corresponds to an association, right? And then what you do is you build this transition probability from a state J to a state K based on the relative frequency of the sequence of states that you have in the state history of this specific client. We do that per client. So, and the history could be either 24 hours if there are memory requirements, because you essentially build this predictor at the client, at the device, that saves the association, the last associations, either of the last 24 hours or the entire history, and based on them builds this chain, Markovian chain, and makes a prediction. So what we saw that this prediction can be quite good. So even if you use only one state, because then we tried how much you can gain if you use two states, not only the current one but also the previous one to make the predictions. And how it differs if you keep longer history or only the 24 hours. And we see that the difference is not incremental, but this performs quite good, around 80% or more, even for the very mobile users. So for this reason, we differentiate. We also tracked the top 5% of mobile where where here the top 5% means using the total number of interbuilding transitions that they had. This is one way. You could choose a different metric. So this is one result. Now you may ask me, well, if you really want to do something very naive, that is, you predict that your next association is going to be the current one. That's the most naive that you can do, right? You don't do anything, you predict the current state. How well you can do, because, you could be suspicious of this result, or you can say, well, how good is this result if the other one, where you don't do really anything, can give you the same, a high probability. Well, it performs pretty bad if you do that. It doesn't perform more than 40%. So I forgot to interpret this plot more carefully. So here you see the number of associations of the clients, and here you see the mean percentage of the correct predictions. So you use this transition metrics every time you predict your next association, and here you take the average of the results. So another thing to mention is that a point here may correspond to a different number of clients, because not all of the clients had the same number of associations. You can have some visitors, for example, and actually, interestingly enough, we had 27% of the clients had they didn't have more than 4 associations, so we call them visitors. So you do have such clients. So actually, to be a little bit more, 8,000 number of associations, you could have 31 clients with at least 8,000 of associations that you can use to do the predictions. Yes?
When does my next association happen? Is my next get?
Oh, no. This is the device. So you see what's happening really is that the device measures the signal strength, and when the signal strength is that it receives from the access point, right? There's the MAC protocol. I'm sorry?
It's going to really change my access?
Yes.
But then when you say with the naive prediction, we assume that we stay with the same access point. I cannot associate with this information.
Okay, let me be a little more clear. What I really meant is that if you have your you have your history, you are a client, right, and you have the history of the associations, what you do is at some point you say, I'm going now, I am in this I have this association, but I'm going to predict my next association. One possibility is to say, I don't run any algorithm, I'm going to predict that my next association is the same with my current one. I don't have any prediction. I just say that my next association is going to be the same access point. The next access point is going to be the same one. This performs not more than 40%. This algorithm, what it does is, it says, I'm building this trajectory metrics, right? The transition probabilities. And I use my history. It could be 24 hours history, or a different algorithm can use the entire history. I mean, the same algorithm, but different input, right? And make the predictions based on that.
40%, of course, 40% means 40% of users don't change their access point.
It means that in average, a client that uses the prediction that the next association is going to be the current one, 40% of the times it predicts correctly that the next association is the current one.
What is the time interval like for the next?
Okay, good question. Okay, 1 second. Okay, so conceptually you can view that there are two types of algorithms. One algorithm is to do it every time that there is a new association. Before that you predict. So when you predict that the next association is going to be that access point. This one way, as I did in this specific plot. A different way to see is to do it in per time interval. So to say that I run this, I poll. You see, you poll every 5 seconds. And what you do is, every 5 seconds, you build your history by saying, where I am now, I keep track of this, of my position. And then, I also predict from the next. I may not change the next, I may not have a new association after 5 seconds, but I do that in a polling basis. And the results do not change, but you can find more details in the paper. But the metric is pretty much similar.
But going back to what you were saying, like, how can you compare, for the first method, how can you compare this result to the result where you don't make any prediction, and you stay, like you say, the next prediction is the same as the state as the current state?
Yeah.
So if you had a verifying time scale, for example, then predicting the next state would be correct, you would think, the majority of the time.
Yes.
Because people change after some period of time.
Yes,
so
right.
if you're polling very frequently, everybody stays where they are.
Right. So it depends. So is this the time scale what you are asking?
So basically, like, you cannot, if you're not changing, like looking at a time interval, you really cannot compare.
Well, but you see,
with next
yes. Well, these results and what I said about the 40%, these results are for every time that you predict the next association, right? You don't have any polling. You say, I don't know when it's going to happen. Actually, this is going to be the next results. What is the duration of how you model the visit duration?
But still, over what period? Because when you say 40%, it means 40% of the users never moved their association.
No, what it means is that this is the mean of all the users, and it means that 40% of the time the user stays at the same access point.
But at what time? That's not clear.
It is per change. There is no concept of polling here.
If there is no change, how do you define that? So if there is no change, so you run this observation, let's say for 1 day or 10 days or time t.
Yes.
And you say 40% on average, there was no change. So there was no change over the time period.
Yes.
So it depends on the time period. That 40% would change. If that t was very small, that would be probably 100%. And if this t was very large,
but you see, okay, but this is implied. The changes are the associations that occur during the tracing period, which is a period of 2 months. 2 months entire period. And how often you had a change to an access point, to a different access point, it really varies. Well, actually, I can show you how often this takes place. So basically, what is the visit duration?
But do you agree that the choice of the period, whether it was 2 months or some other time, would affect the
Of course,
numbers?
yes.
Okay. And so for what number
And also,
period were these results?
These results were considering the 2 months tracing period,
2 months.
having a small warm-up time of the system, so we didn't really include the predictions of maybe 100 associations. I don't remember the exact number now. I need to go back, but there was a warm-up period, and then you start building your history and using the transition probabilities to predict.
So the 40% I can interpret as over 2 months minus the warm-up period. On average, 40% of the clients did not change association over 2 months.
Right.
Yeah. Okay.
Yeah.
So do you have any idea of what is the average number of neighboring access points like in your
Yeah. Yeah, this is an interesting question. I don't remember offhand the number, but we do have, yes. Yes. I would say, so you mean, when you say neighboring, of course it's a kind of tricky question, but if you mean how many access points in a building, like...
So if you are connected to an access point currently,
Yeah.
the next step, how many can you connect to?
Yes, so... I don't have the number of hand, I don't know if we really measure this, but that was something that, we wanted to observe. Because we are trying also to see how, basically, when you construct a graph, and I'll show you an example of this, where we have the transitions between access points, we wanted to find some information like the degree of connectivity, such things. So this is very related to what we are trying to measure. This is a current work, so I definitely don't have the number of hand. But I'll show you something a little bit related. Okay, so I think I need to run now, but let me give you, this is a graph that shows you how you can model the session duration. So essentially the continuous wireless access. So you see this graph for stationary and mobile sessions, and actually depending on the mobility, again, how many edges or interbuilding mobility that you have. So one of the results that you can see here is the more mobile is the session, the longer the duration is. And if you observe, for example, the stationary sessions, which is the black line and it's close to the kind of this bluish line. What we saw is that in the beginning, the decay of this distribution is a power law with this parameter, let's say alpha. And then at some point, at this breakpoint, in the vicinity of the breakpoint, which is the kappa sigma, the decay changes and becomes more close to this vita, to a different parameter. So my statistician collaborator told me, this looks like a Pareto, a distribution from a Pareto family, where essentially the main idea is that, like how the power laws are, so you can, in the log scale, you can have, in the log scale, you can have a line. Instead, in the Pareto, what you observe is that you have a line here, and then like that, and then in the vicinity point, you can have another line like that. But of course, you forget that you don't need to worry necessarily about the tails. So, and using the maximum likelihood, he was able to approximate these parameters, namely the A, B, C, and K. Another metric is to try now to observe how what is the visit duration. And we observe actually quite the opposite trend here now. That is, the more stationary is the session, the longer the duration is. So you see now here, for example, if you compare the black line, which corresponds to stationary sessions, namely sessions that they didn't change an access point, so they remain at the same access point, as opposed to the very mobile sessions, which are, let's say, the red line, which is the multiple edge sessions. And also this looks like maybe you can have a better distribution however, by Pareto distribution can also model the visit durations. Another related question is how the building type could affect this visit duration. So, for example, we have a visit duration, a visit that happens at an access point in a building, right? We have the building type. We know that it is dining or a library or academic environment or a cafeteria. And what we found is that there is a statistical order that exists. So, for example, you can observe in the left plot that corresponds to the stationary, whereas the right one corresponds to the mobile sessions. You can observe that a visit in, for example, the residential visits are quite longer than the visits, for example, in the dining. And that confirms our expectations, right? that we would see this statistical order. And you see similar statistical order for the mobile sessions as well for the stationary sessions. Another question that we're asking is that you have now a session, you have these different visits, right? And you want to see what is the distribution of these visits. Are these balanced? Does the first or the last visit, are the first or last visit different from the other visits within the session statistically? Are they very small? Are they very short or long? What is the majority of the visit durations across the session? So, for example, we have this definition of transit sessions where we talk essentially how small, how short are the visit durations within a session, and this is a threshold for how small is small. So, for example, here you see that a present session with 15 minutes means that all the visits of that session are 15 minutes or less. And you see actually that around 50% of the sessions are transit. If you want to make it a little bit more strict definition, of course you are going to observe a smaller number of sessions. Another interesting thing to observe is that these visits are highly imbalanced. There is a high heterogeneity, variance across the visits within a session. So, for example, you see that we define the session index similarity to be the percentage of visits in a session with duration within an interval 10% from the median visit of that session. So essentially what we're trying to do is, if you find the median in a session, the median visit of a session, how it compares with the visits in the session. And you see that most of them are really outside of this interval. So 60% of the sessions have at most 10% of their visits to be within this interval. So the majority of the sessions have a long visit and there is a short visit duration. And actually we didn't also observe any statistical difference between the first or last visits from the other visits within the session. Another question, one of the last issues that I would like to discuss is the off durations, essentially the disconnection time between two consecutive sessions of the same client. And what we observe here is a histogram. You see a histogram, and what we observe is that there is a relatively large percentage of very short off durations, disconnection times between two consecutive sessions. And we try to see these very short sessions, the clients that have this very short session of durations, if they have any particular characteristic, and indeed 20% of these very short off durations corresponds to 22 clients that most of their off durations were less than 5 seconds, and this could happen due to the loss of signal. Now, then the next question was, okay, good, right? Could we use these measurements to correlate with the access points or locations in the campus to try to predict the sort of like spots with no connectivity? We didn't go very far, but it's still ongoing work. So essentially, to try to see if there is if we can use these metrics to find the areas that we need to deploy more access points or change the placement. One of the last issues is related to the spatial locality. That is, if a user moves very far from an access point, can you define an access point for a user, a home access point for a user? And of course, you can think of different definitions based on the number of times that a user visits an access point or the total duration that the user spends at an access point. And you see that for example, around 30% of the users have an access point when you use a threshold of 75%. That is 75% of the times that these users access an access point, it is the same access point. And actually, you can see that if you use the number of visits definition, this is a little bit more tight than the duration-based definition. This is another graph that shows you the locality of the transitions. In this map, you see the coordinates of the different buildings, and actually a star corresponds to a building. And basically, there is an edge between two buildings if there is an interbuilding transition between these two buildings. And if especially you play with the threshold, so for example, this graph shows it's the same as the previous one, but only showing the edges that the number of interbuilding transitions correspond to the 75 percentile. So as you increase this threshold, the 75 percentile, you can see the hotspots of the campus. So here is the 90th percentile. And if you know the UNC campus, you recognize that actually these buildings that I have indicated there are really the buildings where there is a majority of the user activity. For example, the Davis Library is the undergrad library, the Lenoir Hall is where there are many dining halls and some stores, and the Caldwell Hall and the Manning Hall have some academic, some classrooms, etc. So based on these graphs, you can play with the degree of connectivity and some other metrics. So to conclude, this essentially in this research, what we did is we proposed a novel approach to generate and a methodology to generate these sessions and characterize them using different metrics, trying to classify the sessions on the client based on the mobility. But it is an important issue of how to describe the mobility. What mobility means when the only thing that you have is associations. We found some interesting trends. For example, as the session mobility increases, the visit duration stochastically decreases, and the quite opposite happens in the case of the session duration. There is a statistical order for the different types of buildings, both in the case when you are conditioning on the mobility. We found several interesting characteristics related on the metrics of the sessions and the durations. We found that we can model using by Pareto distribution the visit and the session duration. And we are very eager to extend the study by including some additional measurements. For example, packet losses information, signal strength information, or even information related to the type of the device that you are using or the application that it's running. And then extend the study having traffic load information and have a better idea of the different classes of clients that use the wireless infrastructure. And most important, and this is one of my focus this year, to try to contrast these results, this analysis and the models with traces and analysis from different environments, different settings. For example, a medical center traces from a metropolitan area and also a research institute. And last slide, just to announce the mobile peer-to-peer computing workshop that I'm organizing. This is in conjunction with the IEEE the International Conference on Pervasive Computing and Communications. And you are very welcome to submit your paper if you have any relevant work. The deadline is October 2nd. And we have an award for the best paper, and sponsored by, I believe, by Panasonic. Thank you.
Thank you. Of course, there will be the usual roundtable discussion opportunity at between 2 and 4. So, Dr. Papadopouli will be in the library of the CSCHN building, so you can have more in-detail discussion if you will, but we have time for short questions. I have one. Of course, whenever I see measurements, I want to ask, what are we going to do with these measurements? How are we going to use them to improve something?
Yes.
And as a person with communication theory background and interest, what I'm thinking is that it would be very useful if you can identify how many of those transitions are due to actual mobility or because of signal strength filtering, because that would give a way of assessing how good 802.11 is compared to other alternatives. Because then you could simulate alternatives and see whether you would have that many, how statistics would change, would it be better or not, just from the communication theory perspective. There are other things about designing your support and the caching and all these things that you mentioned, but 802.11 is not God-given. In fact, it's pretty, it has pretty poor properties.
Yes, especially in energy conservation, right?
And so I think those measurements could be used, but you would need to assess in order to start thinking in those terms. You would need to assess how many of the transitions are due to actual mobility or stationary, but they change it.
So extending it potentially with signal strength information or...
Well, the first thing for your measurements, knowing that you're using 802.11 and with fixed powers, then if you know that, let's say, 60% of those transitions were, and you had some numbers like that, which were, but how were you able to determine that they didn't move actually?
We cannot. This is the thing, that you have 8,000 users, right?
And you control experiments, to do controlled experiments. Where
So to hire users.
Yeah.
Well, this is
this is key, because
I-
if you
yeah.
get your hand on that, then you can simulate an alternative program.
Right.
Not 802.11.
Yes.
The same mobility pattern you observe, the same
right.
everything, but with a different protocol.
Yes. So we spent some time to try to think of this and how to solve it, because I absolutely agree with you. And we found the following alternatives. One way is to do a much smaller scale of study with respect to the user population. Instead of having 8,000 users that we have here now, to hire, let's say, 50 users that use the 8.11 and mark their actual positions in some ways. This is one way. Another alternative is to use the positioning system that we are building.
But that they will be affected by the other non-marked users, though. In other words, how many times their signal will be lost and so on. You cannot attribute.
But still, that gives you an indication of the performance, right? Because it doesn't, like, in the end, what you want to observe is the movement pattern of these users and how...
Yeah, but I'm saying that the fact that they will be losing connectivity to an access point will be affected by the non-marked users who are competing with them and are causing the signal to be lost. So.
But always this element will exist, right? I mean, always in the background there are other users who are competing for the boundaries.
Just hiring a few, I don't know, but anyway.
But in that way, if for example, you can mark the positions by, let's say, hiring some students or users to use the system, you can have a better model for their actual movement and their actual location. So you can answer better this question when there was actually mobility, instead of using heuristics as I used in the study of the range or the interbuilding conditions. So then you can say, in this environment where, of course, there are other users that you couldn't control, but that's okay. I mean, always you want to have this in the background. Our users use the 8.11 in this way, and they had these patterns, these association patterns, for which you can, with more confidence, talk about. Or use the positioning system. Ask these users to essentially configure the system using our positioning system or another one, and have this extra information about their actual position. This is another way. The problem there is, of course, that you need to have a very good, a very reliable, accurate positioning system, and this is also a research question, So, any other questions?
Again, 2 to 4, anybody wants to talk to Dr. about a push or video?